So a very good day to you all and a warm welcome to today's webinar, a collaborative effort between Structural Design Institute, more commonly known as SDI, and our esteemed partner, Civil and Structural Engineering Consultants Private Limited. If this is your first time with us, SDI is an education institution that has a lot in store for you. We specialize in engineering covering areas such as design, construction, and software training. What sets us apart from our close affiliation with Civil and Structural Engineering Consultants, more commonly known as CSEC consultants, a name which is synonymous with excellence in the field, having worked on several iconic projects in Sri Lanka. We are committed to the professional development of engineers. So we offer CPD courses and events for those pursuing chartership or looking to enhance their skills. You can see a few of our ongoing and upcoming courses over here. We are focused on structural analysis and design, architectural modeling, and even some courses focused on specialist topics. What sets us apart from other similar organizations is our exceptional faculty, as our educators are all practicing engineers with extensive real-world experience, some of which who are even renowned in academia, like our keynote speaker today. We also offer a set of publications, including the Tall Building Guidelines for Sri Lanka and the Construction Specifications for Tall Buildings in Sri Lanka, as shown on the screen, with more to come. These books encapsulate our team's wealth of experience, diving deep into design and construction specifics. On a side note, we would like to announce that tomorrow, the Sri Lankan chapter of the Council on Tall Buildings and Urban Habitat, which is one of, if not the most prestigious organization for tall building professionals across the globe, will be conducting the CTBUH Colombo Forum 2023. They have an excellent lineup of keynote speakers for discussing some of the most important global topics in relation to sustainable cities. All tall building professionals are encouraged to join. The link to the event will be shared on our LinkedIn page, and it'll also be shared on the WhatsApp group. So today we are conducting the 7th session of this free webinar series, and our keynote speaker will be familiar to those of you who joined our workshop on the design of structures to withstand extreme loadings, which was held earlier this year. We have with us Dr. Damith Mohotti, a chartered structural engineer with over 20 years of professional experience. He's a visiting associate professor at the University of Wollongong and a senior lecturer at UNSW Canberra. Throughout his career, he has actively participated in numerous research and consultation projects and has established himself as one of Australia's emerging scientists in critical infrastructure protection within a very small time frame. He has engaged in many different research projects in this area and has won several project contribution awards. Among them, the highest achievement being a member of the Eureka Prize winning team for Safeguarding Australia in 2013. Dr. Damith is currently recognized as one of the leading researchers in advanced numerical simulations. Therefore, today's session promises to be an insightful one. Thank you so much, Dr. Damith, for joining us today. And I will now hand the session over to you.
Okay. Good afternoon, everyone. Thanks for the kind introduction, Aisha. I'm Damith Mohotti from UNSW Canberra, like one of the senior lecturers from there in civil engineering school. I also attached to University of Wollongong at these days, working as an associate professor there. Thanks again for inviting me for this session. Today's session is more into one of the strength points, which is on finite element modeling. I'll take you in a journey that maybe you didn't come across in your careers. Slightly different to your day-to-day business, especially working with building and bridges and other things. Slightly different area, will be completely different to tomorrow's talk in hydrogen side. But let's see how it goes. I represent my group, Advanced Simulation and Design Group at UNSW. At the moment, we are doing 2 things. Blast, impact, related work mainly, but I am interested on anything related to smart materials, concrete, and so on. But focus for today is more into advanced simulations, but I will call it as high-end simulation capabilities. To get the start, I like to give you an overview of our capability at this moment, especially in 3 different domains. I'll take you through a journey today on the ballistic side. So I will start my discussion with this capability we developed over the years on computational fluid dynamics. Generally, use computational fluid dynamics to model wind behavior around buildings. This is a mechanism that has been used many years in different other disciplines, such as aerospace. But as civil engineers, we always think about, I normally say, node-to-node connection between line bodies. So that's our favorite domain, but we are very reluctant to go beyond that. I like you to think beyond that level in your future. So something I wanted to do in this CFD domain, this idea came a few years back, I think, when there was a consultancy work, Professor Priyan started and gave me a ETAPS model to have a look to analyze the building. I said, like, this work anyone can do from Sri Lanka. So I need to think about something different. So what I did, I actually explore this domain, computational fluid dynamics. Can I use it to predict the wind load on the building? We went over last 15 years, we went along this line. Now we have the capability on capturing most of these phenomena, including, as you can see, some of these animations, the wind flow around the building, as well as the next slide. So, the building responses as well. This is the important part. I consider when you couple CFD with building behavior, that's what we can achieve as a structural engineer in terms of finite. There is a maximum level we can achieve. What you are doing is surrounding environment coupled with the structural model, get our responses within computational domain. It's very similar to what we are doing in wind tunnel, but as you know, wind tunnels are not available everywhere. So we do these things in our group regularly. The next item I like to highlight before we move into today's topic, the capability we developed on blast modeling. This is a experimental work I did last April when I was here in Kalpitia with the help of Triprocess. Actually, they helped me a lot in terms of this program. We tested something we call in band beams. In Australian construction, we call them shallow beam general term. So we tested them for 5 kilograms of C4 charges in Kalpitia for their performance against blast load. What I want to highlight in this forum is the capability we developed to capture those shockwave phenomena, reflections, as well as how it interacts with the structure really well with the computational modeling. So this is important in modern world. Defense play a big role in terms of infrastructure development in developed countries. When we are moving as Sri Lankans into that domain one day, so we need to think about beyond this box, what we are thinking today, and think about these aspects in your design. Furthermore, if you want to couple that one with the structural performance, this is, you can see the track formation and all these things prediction with the blast pressure waves. It's clearly possible within this advanced simulation capability. This is not just animation, which attracts many YouTube viewers or we call it subscribers. It's just for academically sound animation, which has some basis behind this beautiful animation. It's beautiful, yes. For me, it's really beautiful. Same as it has a value generally. People 20 years back call these things as black boxes without knowing what is happening inside. But modern context, engineering is moving in that domain. So we need these things to be successful in developed world. If you don't have that capability, you won't be able to survive. I think the left-hand picture is where your comfort zone. Most of, especially structural field, you are familiar with more than me in this topic. You can teach me on that. It was a good user in it, okay, some years back. So this one is what I like to take you, the right-hand side. Something not that familiar to you, slightly different modeling technique, but still it has structural, material, and other concepts together in one domain. And I consider the direction we are heading today as most complex structural engineering problem. One of the most, I will say that way, one of the most complex structural mechanics problem that we have on our. I will justify this at the end of the presentation. So I will keep it as still a simple statement. The ballistic simulations I consider as one of the most complex structural material problems that we will face or we will solve in our. Today's presentation, I will focus on these elements. I won't read them. You can actually have a look into that. I will guide through, or I will take you through a journey that you understand steps involved in these high-end simulations. Even if you are not interested in ballistic, these things will be useful in your career in other numerical applications. Even it as well. Okay. I like to start this steps involved in with simple clay sculpt. Now, if you think that you are making a face out of a clay ball, starting point is what? How you start? Take a small clay ball. Then try to develop features gradually until you are satisfying with the face of that person or object. This is our kindergarten learning we got from our kindergarten classes. High-end FEA is very similar to this process. It's not a magic box or something that you put something from this end and your meat comes from other end. It doesn't work like this. So you need to have that ability to create this gradually and get the object you want at the end or results you want at the end. People understand this as a black box some years back purely because they didn't follow this process clearly in their approach. So it's very similar to this simple clay ball things we played in kindergarten. So you need to follow these steps to make a good finite element model. First step is start selecting the suitable numerical approach. This is the step one. Don't jump into any numerical simulation without thinking a correct plan. I have seen this happening many students and the groups. They just jump into the simulations without thinking or having a proper plan, selecting whatever available for them. It's not going to work. So number one is select most suitable numerical approach. Then you need to spend time on geometry creation. Third one is mesh creation. I consider 60% of time will be for this one. I know it's a painful exercise. If you have done high-end simulations, any domain, you will face this one. Mesh creation. Good mesh means you have a good numerical model with you. There are many YouTube videos on numerical simulations. You can see those are, I call, generally I use a word called garbage animations. Okay, now, so it's not good for this forum. I think you can exclude that. Okay. So boundaries, you need to define correct boundaries as we all know in even simple PM model, then contact definition. Let's see how we get this one. So there are various numerical methods available. I'll take today's discussion is focused on giving a ballistic as an example, because I consider it as the most comprehensive analysis we are performing when we think about blast, impact, or any other simple earthquake or other simple analysis. Because of that, I thought about taking this as an example, explain the process to you. So there are various methods available. Grid-based approach, generally that's what we are familiar. You can see there's a grid. We create a mesh there. We call it grid general. So we call that method as Lagrangian or Eulerian. There are some small differences. I won't go into detail on that, but this is one approach. If you see this, the other one, the ballistic simulation using SPH, smooth particle hydrodynamics approach. The particles are representing the material domain. So material volume represented by the individual particles. The advantage of this is when you don't need to delete material to represent the material failure. They are moving in the space or within the 3D space, allowing deformations to happen. But the SPH type of technique is very computationally expensive to run unless you are certain that you need that method. Should not move into that domain regularly. If you model something like explosion in a sand, for example, landmine explosion happens within a sand soil. So you may need SPH to simulate the behavior of sand under that high-end explosion. So these are the techniques. So we need to first step is we need to select what is the best approach for us. Number two, once you select the approach, you need to think, should I do this model in mesoscale, microscale, or macroscale? This is something I have seen many PhD students are making mistakes in my group as well as many other groups. Every time they jump directly into maybe microscale or mesoscale. Maybe they don't need that. So you need to select that right domain. What are the differences between these three methods? What do you think? What do you understand by microscale model? The example given here in this slide is in ballistic impact, a bullet penetrating through a fabric system, generally Kevlar fabric, generally armor level fabric, a projectile penetrating through that system in the middle ones. The corner one, it's metallic plate, again the ballistic impact. What do you understand by microscale model? Anyone wants to guess it? Yeah, so we go into the very detailed level, like fabric, general fabric piece, there are yarns. Within yarns, you have fibers, right? So you model even fibers in finite-element to make it to yarn into fabric. So these are the three stages. So if you go into fabric level, fiber level, that's what called microscale. Sometimes we need it. Mesoscale means you go one step upward. We are not going into yarns level. We collect all the the fibers. We model it at yarns level. You can see one of the simulation. I will take some animation on this one later. Macroscale. Think about simple plates. We are not going into detail. We model them as plate, either shell or solid plates. We just represent our fabric or metallic materials using shell or solid plates. That's called macroscale model. So you can see there are various approaches. So we need to select the right one based on Number one, computational resources you have. Number two, capability you have within you. Third one is what most suitable for your work. So this is something clearly misunderstood by many engineers in our field. And this is a great example to show this how we do this. These are what some work we have published recently in 2021. You can see this is a mesoscale model. This is a piece of Kevlar fiber generally used for personal armor, similar fabric. Okay. So we have gone into that yarns level, topology and everything nicely created in the geometry, mesh it properly, and use it for penetration simulations. This is a great example of mesoscale model in ballistic domain. So next step is good example to talk. Okay, bigger pen. Okay, now so right, so working with 1D, 2D, or 3D domain. This is something happen generally when I get a PhD student. Within first few months, there are complaints about, so I need HPC access, high performance computer access. Why? So my model is this amount of elements and it's not running in normal computers. I think you may get same thing here, right? So 8 months. So I say like, okay, we don't need it. Just try to simplify. Most of these models can be simplified, into very simple model technique. Either 1D, certain models are there, we can easily convert into 1D, 2-dimensional, or 3-dimensional models. Simple example is given in this left-hand side of the slide. Circular plate impacted by a projectile. You have circular plate and a projectile, symmetrical projectile. Do you really need to model this in 3D? Can you think about it and tell me? So you have a circular plate, you have a bullet. Projectile word is not that familiar to you. So real bullet, okay? So what do you want? You like to do it in 3D, 2D? What is your choice? Anyone from the structures? For me, it's a 2D problem because you can easily get into 2D axisymmetric model arrangement, considering the symmetry about each axis, and reduce your time at least by 90%. 90%. So do I need HPC now? No. Simple laptop like this can run this model in few hours. My domain is slightly different. Okay, now I'm only worrying if model is running 10 days, at least thinking about it. Okay. When the student says takes like 4 days, really good. Okay. 1 day, almost forget about the model, improve. Okay, because these level models should have enough data points. Data points means the grid arrangement to capture the information. Because this is not magic. Okay, this is not like Hollywood movies. They're not creating animations. There's a calculation or matrix performed behind the scene. Matrix formed by the grid points you have in the model can be properly arranged in a square shape or even other shapes. So think about it when you are selecting a modeling approach. Think about whether you are going with 2D, 3D, or even sometimes 1D. Think about complex scenario like this. This is a cricketer's helmet. Okay, now so this idea came to me because I'm a big fan of cricket. Okay, now it's slightly going away because of the recent performance of Sri Lankan team. Okay, still a Sri Lankan fan, not Australian fan. Okay, now so anyway, now when after Phil Hughes incident, like this incident, he died with a ball. In fact, I wanted to have a go with and see with what is the pressure that a cricket ball can apply into a cricketer's head. It's very simple. It just went with the hobby. Okay. So we did experiment program and we did some comprehensive numerical model. Now you can see this problem is not symmetric. It's very difficult to think about symmetrical arrangement here in this. So can I go for 1D or 2D model for that? Most likely, no. Right? So even that, okay. So if you see this part, the animation here, the level we went into modeling, I will discuss this a bit deeper. Even brain, then the skull, and those parts were modeled within this. Okay, now it's a comprehensive model type. So and then we hit with a ball, even cricket ball, you can see internal parts are modeled. You're familiar with cricket ball. It's not just a leather, it's just a leather cover plus internal core as well. So these kind of complex model, you can't do 2D conversion easy, unless you are super intelligent and find a way to do it. Something like that, you can easily convert into 2D model. If you want to stay with 3D models, you can go ahead with quarter model or half domain because it will save computational time by big margin. Sometimes we need this 3D domain purely because some material models, which I will discuss later, at this moment, just remember the name. Material models need 3D elements, otherwise it won't perform the analysis. Any questions up to this point from either audience here or online? Before we move into the next one. Yeah. From all of you, especially structures people or even architects or something different, something maybe interested to you. Okay. My question, sir. Yeah.
Building structures, what's the scale and also the scale of data, we have data to scale, like scale is scale.
Yeah.
Like scale, so like building structures like your bigger sample.
Yeah. Yeah.
It's the level of detail.
So definitely you can't go to micro or meso scale for that kind of thing. So it's beyond that level. Okay. So there's no meaning of go to macro level or micro level. Okay. So sorry, micro level, because those kind of details in a building model is not required. But if you think about example like this, previous slide I showed like something like this, but this is a specific biomedical engineering problem, but there are certain things you can come across, say vehicle impact in a column. So details are necessary there. So you need to go one step down from that large scale model. No meaning of running node to node like type of column, line body, and hitting with some. You are not getting anything. I'll show you a good example, then I will explain it as well again. So you have a column, just 2 nodes, and line body. Then you are putting an impact load at the middle to represent the vehicle. It's not going to give anything. Just satisfying our heart. So we did something for the project purpose, and okay, and your boss will sign. So then done. Okay, now for me, it's all garbage. Okay, now so for me, it should be analyzed in a proper way. There's a big material part behind this. How material responds, how car is deforming. There are many consultants doing this in industry and earning money. Okay, now doing like impact load like that. Just putting a point load and doing, not considering any other details and analyzing. The world is open for anybody, so there's no restriction on those things. Okay. Any other questions? Yeah.
So you were saying we need to first identify the scope, right?
Yeah.
So for example, if you were to take flat surface and projectile routine,
Yeah.
that sense scope is limited.
Yeah.
But if you were to think about the components of projectile, the composition, the layers, and all of that, in that case, the same scenario, but you would maybe offer readings.
No, we can go for 2D as well. Yeah, even then we can go and model as a 2D object. There are many examples I can give, like we have done it for 2D domain. So we can do it, just need to select the right element formation and define the geometry correct way. So for example, now this one is a half model, okay, of a projector. Now this one I can do in 2D. Cut through this, the center axis and consider as a 2D model, and I model the plate or the object in 2D as well. Give the right boundary condition, you will get the same answer, almost same answer. That's where we make mistake in high-end finite element modeling, unnecessarily going into this 3D. That's why I'm saying you need to think before jumping into the modeling process. Question. Any other thing? Yeah. Yeah. Yeah, this one comes from, like, generally, I will again take you through that path. Okay, geometry creation plays a big role in high-end finite simulation. So we need to select right geometric modeling tool. There are many in the world. Hypermesh is my preference. There are many other CAD modeling tools. So you need to create a good CAD model tool first. So you create that clay ball. You have a clay ball. You need to create that topology and other features using a CAD tool. AutoCAD is not a suitable one. The closest one I can say is SolidWorks. But if you go to high-end, Hypermesh, there's a tool called Hypermesh. It's a real suitable tool. I'm not promoting no advertisement here. But my experience, Hypermesh do the right thing for you, right? So if you get Hypermesh or some other tools to create that geometry, once you create that, then we select right parameter for the machine. So next step is creating that grid or the analysis point. I will explain in there's another slide on that. So that's how we create. So careful, it's same as that sculpture mechanism, okay? The clay ball thing. We develop these things gradually. It's a stepwise process. You can't jump and create this. It's not an automatic button press type work. Maybe you need to create half of this helmet, depending on the geometry, then reflect it and merge the node at the boundaries to get the complete. Sometimes we do quarter mode. So for example, this ball, generally we can do a quarter mode. Create a good mesh for that. Then we rotate it and merge. There are many ways. Okay, now we can talk each one of these elements. We can talk for hours. Okay, now so I'm just touching this area. So to create this, the first step is geometry creation. Then you take this to an advanced tool to mesh. That's some skill that any finite element modeling person should develop in the initial stage of their life. Yeah. Yeah, so totally different to impact scenario. So mainly you need to model now. If you are really after real accurate answers for that kind of analysis, say shock wave for a parapet wall or any structural element, you need to do computational fluid dynamics model. You need to model the air domain. You need to model the structure and show the blast source as well. What will happen? There are tools that can do the job for you. For example, LS Dyna. So, yeah, different from this because there's no object now hitting the second object. Like it's not like a bullet hitting a plate. So you model the blast source. It will generate high energy shock wave with the ignition. It will propagate through the air domain, generally computational fluid domain, and it will interact with the objects within its path. So generally, the problem technically will be solved by computational fluid dynamics basic laws. We call it Navier-Stokes law. So that is the theory behind that. So fluid dynamics problems generally we use for the Navier-Stokes law. Theoretically, that's the formula or the equations we are solving in a fluid flow. So once it reaches the object, it will interact with the object, and information between a structure and fluid domain will be exchanged. And that's how we get the deformation and all these other damage the wall. And so that is the best way we can model explosion in. Okay. So this is an important part in our process. We call it geometry and generating clean CAD models. So geometry creation is a key part in this process, and getting a clean CAD model is a must in having creating a good FEM model. I generally call anything you are downloading from this open source portals, generally they are called dirty CAD model. They comes with different unnecessary features. Okay, you need to spend some time cleaning them before you convert into a finite element model. There are many portals you can easily access and download many CAD models. Some of them pay money, some of them not. But if you are downloading from some of these sources, think about getting into a CAD modeling tool and clean them before you convert into a finite element model. To try to do it directly, you will end up with spending hours and hours into your simulation, because there can be some unnecessary features within your model. Mesh tool will convert them into a very tiny mesh element that can increase your simulation time drastically in your. So number one step is you need to understand what are the details we need in the geometry. Right? So if you think about example like this, this is a cross section of a projectile, NATO standard 5.56 projectile. So you have a lead core, steel tip, lead core, and a brass casing. So if you want to model this, this is the basic requirement for you. There's no other requirement for any other minor features. Say small dent in real one or logo embedded in the real bullet, we don't need it. So when you are downloading the CAD model, they can come with those information. So you need to delete them, remove them, and clean it nicely like this. So you will get a brilliant mesh, something that's given in this. Sometimes it requires to simplify the geometry to suit your requirement. So there are certain areas, specific areas we need to identify. Okay, in our analysis, we need those areas to have refined mesh. Can someone identify from this given example a critical area if I'm taking this bullet for an impact or penetration example? What do you think? Which area is critical for your analysis? Tip. So that's why we have gone into more like create a good mesh there, especially surrounding that environment. And maybe this part, the other part is not that interest for you. Just creating that mass and the momentum for the bullet. So this is important. Identify the critical area and mesh it properly and clean it as before. Then, especially you need to select a good CAD tool when you are doing this business. When I ask some students when come, especially come from Sri Lankan universities, okay, now they started, I can do this in AutoCAD. I know AutoCAD. AutoCAD is not a CAD tool. AutoCAD is good for drawings, not for this kind of work. So civil engineers, we are not familiar with SolidWorks. My group, it's a priority. Okay, you need to learn at least SolidWorks or one of these elements, because otherwise you can't do this work. even civil engineers, it's very useful. This is what I'm saying. Always I'm a big supporter for civil engineering application, but we need to think out of the box now. We stay with these simple elements up to 1000 ETABs. Sorry, I'm using this word, okay, now here, but we are not going to develop our skills. Whenever I meet our undergrads, what I see, so I can do ETABs, I can do SAP tutors. Yes, I understand. But what is the specialty you have to give me? Do you know SolidWorks? No. AutoCAD I can handle. Those days when I graduated, when I first got the job, okay, Shivam knows it. I think job was offered because I knew AutoCAD. At that time, it was a special skill. Now it's like a language. If you don't know AutoCAD, when even I recruited people here in Sri Lanka, when I was working in construction industry, if you don't know AutoCAD, I didn't even send the CV beyond that code. Simple as that. So it's now a general thing. So as engineers, structural engineers especially, do we know something extra? Not, we need to ask that question from us, and something we need to think about and developing additional skills. Okay. So this is a good example for this. What do I explain? I think will answer your problem question as well. This is a CAD model we got. We didn't create it actually. It has many unnecessary features. We clean it as much as we can. Then gradually develop into a mesh model. This is not a simple step. I think it took a few weeks, I guess, if I remember correct. Different tools we try because it was, if you think about the topology of that brain model, there are many small features, different like uneven terrains, okay, many features that we can't easily create a good mesh. So you need to carefully do it and get it. So this is what I'm saying. When you have a CAD model, you need to get into a clean mesh. You need to do some process. It's like you are cooking a good. So you need to add a one. Yeah. Yes. Okay. Can you hear me? Can you hear me? Okay. Sure. Yeah. This is that beautiful model again. The triggered head here. Okay, or helmet. You can see how well we capture these features using finite element in the modeling process. These are few examples. Okay, you can name many like. So this is the important part to have a clean CAD model when you are creating a mesh. The left hand side of the screen gives you a CAD model. When I zoom it up certain area, you can see the problem here. Can someone from audience identify the issue with this model? Yes? Yeah, so this is what I call bad CAD model, and it creates a real problem to the finite element or the mesh model. So you can see the meshes are overlapping, the two parts are overlapping. So this will give you thundering problem in defining the context between these individual parts later in the simulation. You run this is from one of the undergrad projects. They had enough problems with the contact and other things. So they came to me when I checked this zoom in. This is the problem. Yeah.
So is it that the lines are not coinciding? Or is it that there are tiny bits of the yellow part that's going into the orange part? Is that the issue?
Yeah, so it's mainly the both are same. Okay, now so in terms of this, if you are doing this properly, you need to have the same resolution from the both ends. If you are doing this with a good CAD tool like SolidWorks or HyperMesh, they will have that capability of having a good resolution in the CAD model. If you do it, say for using AutoCAD, this one somehow 3D modeling, you will get this kind of problems in your CAD. So penetration, initial node penetration into another part won't accept in your finite element code. the time. Yeah. So now next step is, now we discuss about the geometry creation. Next step is getting that beautiful mesh. This is something that the picture gives you a clear idea. This is a NATO standard 5.56 projectile. How well we created that brass core element, or means, sorry, outer shell. Then inner parts, I showed you some pictures before as well. So we have very good rectangular mesh here, even with this complex geometry. So important is, once you get the clean geometry, you need to define your parameters, mesh parameters here. Can I go for 10 millimeter elements? Can I go for 1 millimeter element? Do I really need to go to 0.1 millimeter elements? Now, not like your ETAP model or other models. I'm not talking about centimeters or meters level elements. Okay, now I'm discussing here 0.5 millimeters or 1.1 millimeter element. Because to capture this kind of phenomena in real advanced simulations, you need to go to that level. Doesn't mean that you will run this forever. Can still get your answers within 1 or 2 days. It's a bad image that people have, that when you go to small elements, you get that time step very low, and suddenly your simulation times is very large. It's wrong. Certain cases we can get answers very quickly if you handle it properly. So parameters, mesh size, and all other mesh parameters should be defined carefully before you jump in to create a mesh. How to do it? You need to select the right tool. There are a few I highlighted here. Hypermesh, ANSYS Workbench. Anyone here familiar with ANSYS Workbench? If you have at least one, good. Should join us. So ANSYS Workbench. When I was in, I think one of the projects at Shiroma work. Okay, now so there's a guy came from, I think, Morat train. He said, sorry, at that time, sir, he said, like, I download ANSYS. We all asked in the room. This is from early stage of Celestial Tower. Okay. In one of the evenings. Okay, now he came to our room. We downloaded means not the official versions, you know, this one. Okay, I won't discuss this thing beyond this because it's legal in Australia. Okay, now so I downloaded ANSYS. He said, are you mad? Because there's no meaning for ANSYS for us. That's what we told that day. Okay. But now if I see somebody with ANSYS knowledge, especially a civilian, not mechanical engineers, they learn. Civil engineer, I consider as a special skill set that person has beyond the other people. Okay, that person downloaded that, and that day we didn't see the value of that. Okay, maybe most of you still don't see the value of this, what I'm saying. But this is the world, this is real structural engineering for me, beyond what we see in our line shell bodies. Okay. Then, when you have that tool ready, you need to think, should I model or create my model with shell elements? Should I do it with solid? You need to ask this question. Or beam elements. Can I do it beam element and simplify certain areas? There are ways to do it. Then refine certain mesh zones. You create different zones. If you see this ballistic model clearly given in the picture, there are small elements near the tip of the bullet, both plate as well as the tip of the bullet. Then you expand your mesh element gradually towards the end of the plate, because we are not that interested of the accuracy of those areas in this particular model. Also, if you are modeling, say you want to model impact on this particular table. Say you are modeling this table top. It's a thin, relatively thin plate when I consider the dimension of this table. How many minimum elements you should maintain in the thickness direction? the thickness direction, you need to maintain certain amount of elements. What do you think about? Have you thought about it, this one, like when you're doing any solid models or shell model or whatever? ETABS gives something or SAP 2000 gives something, we put something, right? Yeah. What do you think? How many elements minimum required? Say you are doing a simple plate impact against a bullet. Plate thickness is 3 millimeters. How many elements you need in the thickness direction as minimum? Or there's no such thing. Can have any number. 1, 10, 50. The guideline is at least in the thickness direction, you should have 3 minimum elements. I will show you an example. Next slide. I will come back to that. Okay. You can see this head model, very thin layers. You can see it here in the blue color one. The other one, clearly 3 minimum elements. More the better. If you can generate more elements within that thickness, it's really good for your analysis. Why? Now, thickness direction, there's a calculation performed in the computer code. Unless you have at least 3 points to do these calculations, you are not getting anything. You can finish the simulation within quick time and tell your boss, like, I did this one and the full answers are there. But it's not going to work. So the requirement is in thickness direction. Now you can see here, I'll take this one. If you see this clearly, these models presented here, the thickness direction of the plate, this is a plate, the steel plate impacted by a projectile. You can see how many elements are there. If I remember correct, the orange color simulation, it's 0.5 millimeter in the thickness direction, 0.5 millimeters thickness of element. So 10 millimeter represented by how many elements? 10 millimeter divided by 0.5, that's the number. So minimum requirement is minimum 3 elements. Then next item is you need to check the quality of your elements. There are any finite element tool, you can run small algorithm and check the quality of the mesh element. Do we have skew element? Or you need to check aspect ratio. Aspect ratio means the longest or the largest length of the element divided by the shortest one. So if you divide them, if your ratio is more than 10, we say it's not good for good simulation array. Like that, there are many other ways to check it. So generally we go for aspect ratio or skewness factor should be checked clear. This is something many finite element modeling engineers are neglecting. They are not checking anything. They put the chicken from one end, get the product from other end, and believe that answers are accurate. So then think about quarter models. Always think about the smallest possible arrangement for your 3D models, quarter model or half model, rather than creating the full model at one. Then if you really need, once you create the mesh, reflect, mirror it, and create the full model so that you will have that full animation. You can see this example. I won't go through detail how well we capture the refinement zone. You can see the impacting zone closer to the projectile, clearly significant refinement in the mesh. Thickness directions, enough elements so that it can capture the material failure. You can see from this left-hand side picture, series of pictures, how well we capture the projectile deformation, fragments. Also. Do we have any questions up to this point? Yeah.
What is it, sir? the practice to design highway bridges considering this impact load in other countries?
Yes. There's a clear consideration for impact dynamics for high bridges, especially because you see large vehicles transporting different goods in especially developed countries, they are massive. So 40-ton, sometimes 20-ton trucks. So they can hit easily in a bridge piers and cause significant damage and road closures as well. They value this because any road closure means money for the government, losing the money. So they need to find alternative routes and they need to arrange some other mechanism to divert the traffic and these things. So they consider this very seriously. Because of that, definitely any major bridges, it's a good practice always to have this one check before we finalize the design. This is something like blast design in those countries. Any infrastructure project, even though it's not visible, they check for blast. Certain kilogram of thread, they check. I was involved in one of the metro project in Sydney. Metro means the train system. We have driverless train above the system. So they have this new train lines and the stations developed in this particular project. All these stations are checked for certain amount of TNT equivalent, the charge, possible threats, so that if there's an explosion from within that premises. So that's similar way for bridges, main threat is, I think, the vehicles, especially bridge wheels. Not only bridges from vehicles, sometimes, especially large-scale boats hitting in bridge piers has caused damage significant. There are many studies done on that direction to analyze and find a rectification methods or even protective measures for bridges. Any other question? As much as possible, go for rectangular element. But try to avoid triangular element, because triangular elements are good in fluid dynamics, not for normal Lagrangian level FE. Because if I try to explain this, it will take a bit of time, but the main argument is when you put triangular element, start to increase your node number within the same volume mesh. So you have 10 meter by 10 meter element, model with rectangular mesh, you will have less nodes. Less nodes means what? Less computational time. You have triangular mesh to have that. It's almost like you divide that rectangle into two pieces, right? You create more additional nodes into this system. And in terms of the algorithm, triangular meshes are a bit more rigid than real rectangular meshes, as proved, okay? So if you consider all these things, I think the best option is go for rectangular mesh as much as possible. Sometimes there's no other choice. We need to go for complex geometries. We need to go for triangular mesh. Yeah. So don't, especially like something like this, what you can see from this slide, we haven't used any triangular element here unless there's a small portion. I'm not sure. I think it's 0 triangle. The head model. Yeah, you can see complex geometry. There's no other choice. Almost brain model, there's no other choice. It's like a fluid domain. And it's not the main. Yes, we want to measure the pressure transfer into the brain. That's the main idea of this. But we didn't want to do any analysis on how the brain behaves under that particular pressure. So what we need is the surface pressures only. So in this case, having triangular mesh is okay. We can go for rectangular mesh even for the brain. It's the perfect scenario. But if you see the geometry here, it's almost impossible unless you simplify it. Yeah.
Consider the ratio of
Yeah, generally aspect ratio, now it's depend on the tool. Early days, ANSYS says, if you are doing ANSYS type of modeling, ANSYS says aspect ratio keeping under 10. So if you have a 2 millimeter length in one element and the smallest dimension is say 0.5 millimeter. So your aspect ratio is 2 millimeter divided by 0.5. Right? So if it's below 10 as a number, they say you are okay to go. But if it's not, try again some iteration with the machine. See whether you can get at least 90% or even 100% of your elements within this guideline. By saying that again, if you go to a complex model as cricket ball impact to a head, sometimes it's difficult to maintain that requirement. So we need to sacrifice that and go ahead and do the analysis. We know that it can add some additional simulation time into our. Is it clear for you? Are there any questions in online? No?
That's a balance that you complicated.
Yeah. Okay, yeah, that's. So this is again the same thing. Now, the example I'm showing here, solid plate, a steel plate, says 10 millimeter thick, coated with the polymer layer as a armor system. How do you think about modeling that polymer layer? Say it's 0.5 mil thick or something. So you have a solid steel plate, you are familiar with that. You have a polymer coating on top of that, say 0.5 mil or 1 mil thickness. How you model this? How do you want to model the polymer layer? Shell, solid. It should be shell. What will happen if you do it with solid elements? You understand this or no? Now you have a thickness, okay, thick plate. Then you have a small coat, say this thickness. Sorry, yeah, can't see, no? Yeah. So what do you think? I think the example given in the picture is more clear than that. So a steel plate and coated with a soft polymer. Polymer thickness is say 1 millimeter or 3 millimeter. What will be your approach to model that polymer layer if you are doing an analysis later? Generally, it should be shell. Because if it is 1 millimeter, if you divide even to keep thickness direction minimum elements, you need to divide 1 millimeter by 3. So your thickness direction element size will go down to 1/3 millimeters, right? 0.33 millimeters. It's a very tiny number. Your plate is big, say 5 meter by 5 meter. You can't get the aspect ratio right below 10. This is what you need to do as when you start thinking about it. You need to think about complete model size, dimensions. Think about the critical elements, it's like something like plate thickness, narrow gaps, and so on, and select that element size appropriately, and select that approach, either solid or shell, and combine them in a single model is useful in any approach. Okay, now we are moving into the, again, one of the most important areas and neglected, and most of you are familiar with. I think you're not familiar with this part, okay, as general structural engineers. I think so. The material aspect in a finite element model. Generally, as a structural engineers, you are very much familiar with up to yield point. Is it a correct comment? Or so you are working in that linear zone. Very comfortable. Young's modulus is there, yield line, okay, reach yield line means it's like a failure for you. Is it correct? Yes. I'm not interested on that zone for my analysis. Last impact or crash or whatever, I'm not interested on this linear portion. It's a tiny portion in my structure in terms of the material behavior. What I am interested is beyond that point. We call it plastic material behavior. That's where the energy is absorbing in a real structure when it undergo heavy load, either blast, impact, or similar. So this is the difference between your general practice as a structural engineer. You are working in this linear zone, but blast impact, you don't care about linear portion. Now can't do anything. What I'm interested in is beyond that zone, especially beyond the yield point, this plastic deformation zone. That's something you need to understand clearly. If you are working in a crash analysis, impact problem, or blast analysis, or impact or ballistic analysis, whatever, similar application, you need to tell you, like your brain, okay, I'm not in that linear zone. I'm working in ultimate strength and the failure point direction. We can't stop the structures failure, like going into yield point with real blast, okay, now then, unless it's far field and small charge. So we need to understand what are the real materials we are using in our analysis and how well we can represent them within the model. So you have a column, you want to reduce the impact damage in a car park by applying a polymer coat around. So can I represent this polymer coating with a bilinear or linear material behavior? Yes or no? You understand bilinear behavior, right? That's what you use in your general analysis. You have actual yield point, a linear curve. After that, it's another linear curve towards it. So polymers or rubber type material, can I represent using bilinear mechanism? Bilinear arrangement is your second picture here in the diagram in the slide. It's called bilinear. Anyone knows how this rubber type of polymer type of material behaves? We call them hyperelastic materials. But first picture here, if you see the slide, the first diagram shows you hyperelastic behavior, stress strain behavior. You can see elastic means it's like you have a rubber band. Linear, then it fails when it reaches the maximum capacity. Hyperelastic, you can see it's a real, the Young's modulus changes gradually, continuously till it fails at the end. There's a clear plastic zone you can identify in the middle part of the curve in a hyperelastic material curve. That's what contributes to the energy absorption in such material. Bilinear, when people are thinking simplifying models, it's good, but we are not using generally in our applications. Almost no meaning. Why I'm saying this? Because whatever you feed into the computer, that's what the computer understands. If I use concrete as a linear or hyperelastic material, it will give answers, but it doesn't represent concrete as a material within my computer simulation. Do you understand this? Yes. So you have a concrete as a concrete material. You want to do a model, say concrete column impact by a vehicle or some other object. Can I use hyperelastic material model for that? No. Because this is not what you see in concrete in terms of compression test data, right? Totally different behavior here in the first picture. If you go to the last one, this is a typical stress strain behavior for a metallic material. Has a linear portion. Once it reaches the yield point, then it's still you have a strain hardening zone. We call it a strain hardening zone. Then reach the ultimate tensile strength and then reduces strength and fail at circle. This is a complete phenomenon of the material behavior. So what we need is understand the materials in our simulation, represent them in a correct way within the model environment. Please understand this value even if you are doing simple modeling like SAP and ETABS or any other tools. You need to do it. There's no meaning of doing models and getting animations or results for the sake of getting them. Because if you are feeding a hyperelastic curve as for concrete, it will give you some answers. You will be happy, so I finished the job, but it's not the right answer. So we need to consider material behavior, understand whether it's linear, non-linear, whether elastic, hyperelastic, or metallic type of behavior, whether the material behaves brittle manner or elastic manner. You need to ask this question from you and select the right material model for your average. When I consider LS type of tool, which I consider as number one in this game, okay. So has 250 plus material model to use in your simulation. As an experienced user for that tool, I only know 10% of that models. Okay. Very difficult. When I need new one, I need to go through the manual and use it. So you need to select right one. Now here I have given a clear example. This is that fabric model or the yarn model we discussed before. To represent the yarn behavior based on the experiment, we have used a simple material model called orthotropic elastic material model available. You can see different parameters, density, Young's modulus in different directions, Poisson ratios, shear modulus, failure stress. We are defining almost everything. Ultimately, when you define these things, computer code will understand the real material behavior, the curve, stress strain behavior within the code. This is your input to the car. It has predefined material model. So almost represent this curve here in this slide. So it will follow the same pattern when the material is undergo certain deformation in using. So you can see, you can now understand the value of this getting the right material model. If you feed something wrong, what will happen? Right. Some answers are there, and you are happy, and your boss is happy as well, and everyone happy, but answers are wrong. Luckily, until next vehicle interpol, we don't know, right? So that's what we say in last. In last domain, we can say, okay, something happened. We say they brought like another 1 kilogram PM. So, you see, I designed for 10 kilograms. In this case, they got 10.5 kilograms. So that's what happened to them. That's the reason for the failure. Okay, you will do that. What I'm saying is. So you can see now whatever we discussed so far. You can see the top part. I don't know this size. Some okay, that's one. Yeah. If you see this one here, this is an experimental high-speed camera images for a ballistic penetration of a small sphere through fabric yarn system, Kevlar fabric system. The bottom here in this image, it's a simulation resistance. Can you compare, spend say few seconds, compare top and bottom? Is it close enough? For the spec animations, okay, now so we are not doing video creations, okay, it's a Hollywood Bollywood movies. Okay, now so I'm creating animation, mathematical animation. It's close enough, right? So yarns are coming out from the fabric. Separation is there. Even this long black type of phenomena captured in the models. So relatively okay. Don't expect it now. Some people try to like get the real animation like Hollywood movies. Okay, now so you are not getting it because there's a physics behind it. The other version, there's no physics. Okay, so you can see how well this capture like the yarn separation, giving that the space to the board. This is all mathematics. Okay, now this is not like just animation. So there's a clear matrix work behind this. Anyone learn those matrices in like mathematics? I think first year, no? That's a very difficult subject, no? So that's what happening behind the black box. It's so called black box. Okay, now so this one again. This is a polymer aluminium system. The gray color ones are aluminium plates and the in between polymer. The aim is to have parts of material to break the projectile and have a lightweight system so that we can defeat a projectile. All the example I'm getting today is ballistic focus. Okay, the work we did. So how well we represent this fracture and the mechanism, you can see we have there's a model called Johnson-Cook material model. I rank it as number 1 for metallic materials. It has capability of capturing the linear portion, strain hardening, thermal softening. You know, like material when they undergo huge deformations like this, material get heated, right? That the heat or the temperature, the heat convert into energy. So material get softer when it's undergo this kind of large deformation. So we need to capture that one in the model as well. So Johnson-Cook material model is a good one to do it. It's available. The soft material, polyurea here, captured by there's a very well like the popular model called Mooney-Revlin model. It has that nice hyperelastic behavior captured through the model. So that's how we do this simulation. So now you get a small feeling why I said this is one of the most complex problem for structural engineering. Now you need material parts. What we learn in 4th year, 3rd year in undergrad time, bilinear curve is the max, right? Maximum level we went up to bilinear curve. I don't know even that one, whether we finish it linear curves or not. Okay, so we need to go beyond that if you want to get simulation. You can see again another simulation. You can see fragments are coming up nicely. So this is exactly what happened in a projectile penetration. So it creates a crater within the system and it comes, and if it is a deformable projectile, it will deform and create those fragments. So these phenomena should be captured correctly if you want to simulate something in this caliber in the field. So material modeling now I think is a key component in this journey. You can see clearly the crater, we compare the test results as well. The dimensions and the weights create the crater, it's all matched really well with experiment. So there are many material models. I think I won't go through into details. You can see from this slide, different materials, you have different material models. You can use it for your application, starting for most famous ones, and there are many new ones coming into the market every year. So generally, these material models generally capture the stress strain behavior up to failure. Now, next step is, you can see from this animation, how well we capture that the yarns failure, right? So when the projectile impact, even internal part gets separated, and then yarns fails, and it allows it to penetrate through the system. This is a real good example you to understand. Now, in addition to the stress and behavior of the material, we need to define or when we need to tell the computer, when the material model reach this stress strain condition, you need to define it as a failure and remove those elements from the analysis. It's like a failure definition within computer simulation. So there are many ways to do it. What you can do is simple strain value you can define as a failure strain. Anyone familiar with concrete failure strain here? According to the Eurocode. Yeah, generally, like I will say milestone. Anyone familiar with milestone? Say failure strength roughly. Okay, now I'm not going to. I'm an engineer, like not working in third decimals. Okay, I'm first digit. Okay, before the decimal. Okay, that's my level. I don't like people to like my students when they put answers like third decimal. For me, I can't. Okay, now so because third decimal in this engineering discipline is wrong. Yeah, we are. Okay, in civil engineering. That's my belief. Can be wrong, but I believe like we are in like before decimal. Because we have multiple safety factors and many other assumptions and so many things, and we do third decimal calculation. To me, it's nonsense. Okay, now so that is that. So can you tell me like what is the like failure strain, like general milestone? Can it undergo 100% elongation? No. So it's like roughly 20% elongation. So when it's reached 20% type of elongation, 0.02 is the strain. So roughly like it fails. Okay, hypoelastic material like polyurea, rubber. Polyurea means a polymer type. Rubber. These things sometimes goes in terms of the failure strain 100%, 200%, even 300%. Still not fail. Elongate. So you need to have some sort of understanding on these things and define failure according to maybe use a critical strain value or stress value. There's a better way to do it. You can define as a maximum energy absorbing capacity is a better way. Energy absorbing capacity generally defined as the area under the stress strain curve, if you remember your basic material science part. So generally what we do is we analyze the material failure curve. So you do a material test until it fails in a laboratory environment. You get that energy value and we input into the curve, a computer code, and say when the material reach this energy limit, define it as a failure and remove the element. That's what happened in that meeting. There are comprehensive failure models which I prefer to use in simulation like this. Capture many other phenomena. So if you are serious in the business, you need to use that comprehensive failure model. Or you combine one of these previously defined model, the discussed models together in a single. Okay. There are various ways we can tackle this problem. Once you do that, you have this beautiful animation. When I begin my journey in finite element model, at that time I was at Melbourne Uni, I went to a project meeting and I saw somebody. This is my starting point for this whole journey. Okay, now in a project meeting, I was like you at that time, only knew like line node connection with SAP and ETAPs, good to download other versions as well. Okay, so then I went to this meeting and suddenly found somebody done animation like this. That moment that went in here. Wow. I haven't seen that kind of animation before. What? As civil engineers, we like those simple model, rectangular domains, not very comfortable, and we are comfortable as well. So when I saw this one, I told to me, one day I need to do this. And I need to do by myself. Okay. So I thought, no, I will get there some one day and achieve that level in ballistic modeling because that's super. Okay, now fragments are going everywhere and bullet is moving. Our ETAP models are not moving unless you do something crazy. Okay, now so it will be stationed, right? Will move slightly, right? So we show analysis type, but otherwise you won't get anything. I like this moving stuff. Okay, now like you can see the bullet is hitting parts are going everywhere. This is real good. So I thought, no, one day I'll do it. Now that's why I'm doing this lecture now. Okay, maybe I followed the right path and got into that layer. Yeah, this I think one of the real example for you all as well. This moves, this visual. Let's need to go back and come back again. So you can see this there's a truck moving in towards a column, concrete column, hitting the column. Other than all these things we discussed, there's another element you need to be careful in this kind of models. What is that? Context. So if you don't define the contact right, again, this truck can penetrate this column and go into the other side. There are many cases like people show us simulations like that. So you have real contact definition. There are complex models for contact definition. But when you have different objects in your simulation, you need to define the context. There are various ways. I won't go into detail, but penalty-based contact and constraint-based contact. These are the two general mechanisms. As a theory, how they differ is how they define the stiffness within the algorithm. I won't go into that detail because there's no interest on those. Sorry? Yeah, no, yeah, that's right. Say, for example, this vehicle now hitting the column, and you can see some elements are going out from the analysis because they reach the failure point. There are algorithms already developed, even with material failure, it's keep that the remaining material to keep the contact with the other bodies. So there are advanced material models. When the material is eroding or the removing from a failure, reaching the failure, still you have the contact between objects. So these are the challenging part again in this kind of simulation. So you can see here, when the vehicle hits the column, it will undergo large deformation. There can be certain failure within the front part of the vehicle. So these materials will be eroded or removed from the analysis to keep the numerical stability. Then remaining part will still have the contact with whenever the vehicle moves closer to that, based on the contact definition, at certain distance, it will start developing the contact with the. Any questions up to this point? Yeah, let's answer that. Yeah. You want to answer that now or patience? Yeah, I'm okay now. Yeah.
So one person asks on page 21, how can you get the two layers connected to each other?
21. Yeah, there are ways to do it. There are context algorithms we call tight contacts and tie break contacts. There are ways that we can define contact between multiple layers. Or sometimes we do it node to node merging. Node to node merging means if nodes are matching from shell plate, in this example plate here, with the underneath solid body, then we can do a quick merge between them. they will share the node properties between two objects. Two objects are here, the plate and the underneath solid body. This is a simple way, but there are some other algorithm already developed. We call it tight context. We define it, selecting nodes, you can merge them together. So there's an algorithm, understand this. So it acts as a bonding agent between two bodies. We can permanently bond them, or we can define a certain stress level. After reaching that stress level, these two parts will be separate. So there's a way to do it. Yeah, we can use link elements as well. But if you think about putting balls or something, generally we use link element to represent the ball in a simple FEM analysis.
Let's not skip the general question. They've asked, when we model a high-rise building, how can we get the effects from the surrounding buildings, such as wind and other impacts?
That is exactly like what I said. Like, so for me, wind analysis performing, giving just node forces is not my interest. So you need to get at least either CFD model run or even do a wind tunnel test and get this surrounding the wind flow interaction into the building. So you need, my preference is, because this CFD simulations has gone so far now, like the distance wise and very accurate level, you can run easily a larger model CFD in CFD analysis and try to get pressures on the building accurately as a time history function and apply that into the building rather than just putting some S1170 part 2 type calculation in code in Australia or Euro code according to your preference and just put a pressure load. I think it won't give the real dynamics for the whole building. This is my view again. Okay, now I always say this one. I'm a big fan of this kind of like detailed analysis rather than more simplification. Because in a metropolitan area, even Colombo now, you think you have another tall building somewhere in between those tall towers. I don't think this wind code can give you anything. This is the truth. Because wind flow will be totally different. So you need to think about analyzing, like running at least wind tunnel model with the surroundings. Or my preference now is, okay, because if you don't have money initial stage, you run a CFD analysis, quick analysis, even with the ranks modeling, not LES, these are very computationally time consuming, and get those pressure values into your analysis as a finance. So for me, surrounding should be considered definitely.
And our next
Yeah.
question.
Yes.
Another person has asked, should a layer in a multi-layer structure be modeled as shell elements instead of solid elements? If it doesn't meet the minimum three-element requirement based on thickness and mesh size.
Yeah, definitely. If you can't do 3 elements in solid layers and having now like if you say, for example, 1 millimeter thick layers, you can't divide into 3 and you will definitely get, otherwise you will get very tiny elements in your thickness direction. So in this case, I recommend to use shell. As long as you use shell, you will be safe in terms of the computational time. Shell elements are not expensive in terms of the computation time. But there are certain cases, your thickness is sufficient to divide into 4-5 segments, and you need that information along the thickness direction, as some of the examples I showed you in this presentation. Then you need to do the solid fill. So it's a judgment any FEA engineer should take at the beginning of the mode. Experience will definitely guide you to that level.
Final question is, someone asked me if it would be possible for you to share the latest slide.
These are like wealth, okay now. So share, he's asking to share the wealth, okay now, yeah. Yeah, most likely, yeah, possible. These are not copied from internet or anything. These are our work over the years. Okay, now it's basically my group work, so not copied from anywhere. So that's why we reluctant to share the presentation slides as well. We go to the last few segments here, like hourglass energy. What do you understand by hourglass? As this top picture gives you, shows you. You have this things in at your home or as own ones. So you have all. So hourglass energy means an error created by numerical simulation. I will put that, it's easy to understand that. So any numerical simulation, if you do it even perfect level, will create certain error because it solves certain equations. You have error margin in those equations. That's why I'm saying, especially the very senior generation. Okay, now they argue, okay, you're not getting that answer. You're not giving real world answers. Maybe 90% accurate is good enough than running Excel or solving through equation. Can you solve this kind of problem in equations? Like, no way. Blast? No. Ballistic penetration? No. So almost no is the answer for most of the questions. Okay, so we need, because it's a thundering amount of matrix, right? Elements running behind this. We can't solve easily by hand, even can't simplify some. So accuracy we can achieve through this one is the maximum we can go as humans. Unless artificial intelligence, I will present something in Candy if you are attending Candy conference, something on wind domain, where we use machine learning as a next step to solve some of the problems. But mainly, so there's an error margin. Error is there. Okay, so what we do is this hourglass energies, that error comes from the calculation. Gradually, cumulative error comes and shows as energy in the system. You know that according to these laws and other things in physics and other, energy can't come from into the system from outside, right? Unless we put something from outside. System energy should be balanced out nicely at the end. So what I'm saying is this hourglass energy in any finite element tool, there's a way that we can create this, we can check this hourglass energy. It depends on the material models you use, it depends on the element formulation you use, and there are many criteria for this hourglass energy. The fun part is sometimes the student create models. This hourglass energy is more than initial energy in the system. Can it happen like that? According to the laws we know, energy can't come like that unless it's a nuclear reaction or something. So if you see, so system should have the balance in terms of the energy. So sometimes, now if you see this black curve here, it shows us internal energy. The next one, the line here gives you the kinetic energy. You see, kinetic energy start from 4,500 and reduces and generally convert into the internal energy. Very simple phenomenon. I think you know this, right? Because of this deformation here, the impactor comes down and hitting and slow down because of the impact. That's what happening here. The kinetic energy reduces, but it converts into the internal energy. I won't go into detailed explanation of this, but now with that time frame, you can see gradually hourglass energy increases. Sometimes this goes even beyond the internal energy. So what do you think about that kind of model? You see some animation results and all these things at the other end. Will it be accurate? No. That's why every time we are running in this level of simulation, you need to check this hourglass energy, see whether it's within the acceptable limit. Generally, we say if the hourglass energy is within 2 to 5% range of the total energy of the system, we neglect any error caused by that. Simple as that. If it's beyond 50%, you are in desperate situation to change the model. No way. If it is more than say 10%, I won't accept even as a model. So slide, you put something, I will have a slide on that. I will tell that time what is that. Okay, later. So this is that. It's a good advice to anybody who's doing modeling. This slide clearly show a different material, how selection of different material models to represent your material can impact into hourglass energy. So there are various factors that can affect hourglass. Your element formulation, your measures, your material model selections, many. So we can't predict at the beginning of this. So what we need to do after running the simulation, we need to check this carefully, see whether it is within the acceptable range, generally 2 to 5% of the total energy as a company. Is there, then forget about this hourglass and go ahead with the analysis. Now, coming to the last few steps, the time steps. It's a beautiful. Generally, high velocity impact time step is 10 to the power minus 6 to 10 to the power minus 7 time. What is time? You understand what is time step? Anyone? General time step is to run one analysis cycle within the computer code, the time taken by the computer or the software, what we call it, code. So 10 to the power minus 6 to 10 to the power minus 7 is very scary. So think about, you want to run one simulation to get 1 second results. 1 second. How many time steps you need? 1 divided by 10 to the power minus 7. You understand now the scary part of this whole thing we discussed so far? That's why this time step influenced by many factors, including the quality of the mesh, material model selections, contact algorithm, everything we discussed so. If you put garbage initially, here, this is the place that you think about your computer. If it's not belongs to you, you think about something like this a day. Many PhD students are like that. Okay, now, so they think, oh, my computer, the problem. Really, computer is okay. We have the problem with us. Okay, we have other ways to tackle this problem, but we blindly go and model something because that tutorial in YouTube says something else. Those guys are creating, like, earning money, right? So there are animation creators in YouTube. Any software nowadays, there are many videos, so we follow them blindly. We get, end of the day, we get, say, 10 to the power 11, minus 11 times 10. Almost like end of the world. 10 to the minus 11. If you want 1 second simulation time, 1 divided by 10 to the power minus 11 is your number of steps or ratio. So it's huge. So generally, impact problem, especially ballistic ones, you get this time step because it's so sensitive to the contacts, the mesh size, and all this. Blast, generally, you get, if you can stay with 10 to the power minus 6, 7, it's a good one. So all depend on, there are formulas for that. Generally, sound velocity within the material impact this. So if you have soft material within your model, definitely your time step goes down. Element minimum size is small. Say I have 0.1 element and you have 1 meter element. You will have higher time step. I will have very low time step. Material properties. If you have elastic module, like the material properties means elastic modulus, Poisson ratio, and other properties are directly impact based on the equation given here. You can see clearly the sound velocity is dependent on those parameters. So real ballistic event, we don't need to run long duration. Everything will be finished within very quick time. So even if our time step drop into 10 to the power minus 6 or 7, we don't care about. Because we just need to run roughly 10 to the power minus 5 seconds type of time frame in a ballistic mode. So it's a small time frame we need. Because what is the real NATO standard projectile velocity? I have open fires everywhere. So, do you know the velocity of a projectile in general? Anyone? Because today's topic is projectile, the ballistic. You know the real gun bullet velocity? The standard velocity, they say 930 meters per second. 930. That's what hit us, or soldiers, or input. So 900, above 900 meters per second means it's serious business, right? So when you do a simulation, your projectile travels that fast, it will penetrate even a thicker system very quickly. So you don't need to run seconds in terms of the simulation. We'll run a fraction of a second in terms of getting it. It's almost like a fraction of a millisecond. So time duration is very small unit in terms of velocity. Blast model, if you think about the structures, you need to get the structural response. You may need to run 100 milliseconds roughly. Thumb rule is 100 milliseconds to get the structural response as well. So duration is large in blast simulation. So should I have smaller time step in blast or impact? Which one is possible? Because blast, I want to run 100 milliseconds. Impact, I can run and get the answers within fraction of a millisecond. So which one of these should have higher times? Blast. Why? Because if blast has a small time step, your waiting time to finish the simulation will be ages, months, or even. Okay, I think your message is clear, right? So this is that. This is what I'm saying, like students or even the beginners, they come and complain like computer power is not enough. I need supercomputer. Oh, when you give multiple core computers, now we have few in our group, so 48 cores or something, then it's not enough again. We need 100 cores. 100 cores given, then it's not enough again. Like that it goes. Okay, now there's no end. So what are the tools that which can use for this kind of miracle type of work? I said miracle because the reason is I like them. Okay, now so LS-DYNA, my favorite tool at this moment. There are like Photodyne is within ANSYS, you know ANSYS. It's a good tool, but they are not developing it anymore. Like it's almost the same as 10 years ago now. Abacus, people are using it. There are differences between LS-DYNA and Abacus, advantages, disadvantages. Nastran, I think NATO was USA, they use like Nastran tool. It's a very comprehensive tool as well. I think, but still by far, for blast impact, LS-DYNA can consider as the world #1 tool that is more. The reason is there are many reasons behind that because of the able that tool has many material models. Algorithms are powerful in terms of capturing, and most important, simplicity of developing the model. It's just a text file we have worked. Even you can open the model in Notepad and edit it. Simple as that. So my advice for most of you, if you're thinking about future as like structural engineers in this country, okay, or even world, think about beyond sub 2000 ETAPs and think about this world. I just want to highlight this one and pass the message to especially the young graduate in this country, because when they come to us for PhDs and other things, I really like to see they have this skill. It's not coming to us only, but going anywhere like UK, USA. It's a big advantage. There's no meaning of we work with simple tools and like run these other things because the world is moving. Okay. So small message, it's not a criticism, but it's just giving that what I know from the outside world. So we're coming to the end. To recap what we discussed, okay, now why I think we discussed, I highlighted this point, I said like I will recap this one at the end. So I consider this kind of ballistic event as one of the most complex problems that any structural engineer can solve in their life, professional life. Why it is considered as that level? We have structural dynamics to understand that part. Material, sound material knowledge is required to tackle that problem. Fracture mechanics, one of the most complex things we learn in universities or even higher, like your masters or beyond that. Energy concepts, we still don't understand even. And you need FPA, like general SPA. So it's a comprehensive package. When I consider all these problems we are solving as structural engineers, I rank this as one of the most complex scenario because of this. Now, this is the message to take today when you are going. Forget about all other things we discussed, take this message. If you have a problem in any finite, you need to understand what you are feeding to the computer. The quality of that material is what comes from the other side. If you feed garbage, what comes from other in this garbage as well. Most of these things, especially for finite element, this is a real. Many 90%, I said in my group, like 90% of the work published in YouTubes and other places are for attraction of subscribers, it's attraction for something else, quick animations, and people get attracted, LinkedIn posts, so the good world is there. But understand there's a world beyond that. So it's all about putting good quality information into your computer. It's not then a black box, it's a real physics, engineering there, then you get the quality product from the other. If you put garbage, what comes from other end is garbage. So that's a message take away today. With that, I will conclude my talk today. Just want to thank all these people who graduated under me, Dr. Lakshita Veerasinghe, Dr. Lakshita Pranal is at Moratuwa now. Dr. Pasun Vijayasuri is working with me still, and many others, especially Sri Lankan dominant. It's my priority to give 90% of my quota to Sri Lanka. Okay, now, not because of anything else, we are getting heavy application from number of applications from other countries, but as a service for the country, I'm giving that priority. So this is my new group at UNSW Canberra, I think all are there, like at this moment. They're doing very well. So most of these previous graduates, they help to develop this work. It's not only my work, and there's a huge contribution from there, especially these three names there. So in addition to that, yeah, any questions? I think I cover everything. I hope it was clear enough. So we'll go to something different and we want to get activities. Thanks.
I actually have a question.
Yeah.
So like you said, now, you as basically you can't completely rely on YouTube, you not get guidance for this sort of thing. So if somebody is self-learning and they're looking for resources, looking for guidance in this sort of thing, then how would you advise them to go about it? Because YouTube is just very easy to access, find some kind of solution, to kind of tackle your problem. So what would you say?
Yeah, this is the challenge now that because there are many people because of the, like this money matter. Okay, now, so there are, I'm not a YouTuber, so I don't know this, I'm not expert in this one, but releasing videos frequently and getting, but you need to check his background. To give some guidance on this direction, someone need to be in that level, like at least that PhD level education background to release something on this matter. Otherwise, for me, it's animation. But there are people doing this good, like learning, self-learn. But what I advise you, select and check the profile of those people who are creating the videos. There's no other way even, because if you are not attending a course conducted by any, these are expensive, okay, super expensive, this course. So the best advice is just follow them and check whether they are from a recognized institute, what sort of education background they have, and are they belongs to this leading expert in the business in modern times. So if these three elements are right, then just follow them and learn their videos or their tutorial. Because I know that there are many others releasing the videos and other things can cause many problems later.
Apart from that, would it be like maybe research papers?
Yeah, definitely research papers. Yeah, if you have the basic knowledge into these tools, I guide you through the research, like to the research papers. Because if you go to a reliable like publications, so you can get the basic framework done. So then once you do that, ask questions from yourself and maybe contact somebody who's doing it properly. So then you can get that guide. You can't spend money on the other training because trainings are like this level is expensive. No one is selling this one cheap because you know the difficulties. So it's tough. Any other question? Yeah, one.
It's that other question that we had earlier. Someone says, I'm doing a 4-point blending test for TRC games using Abacus, but I couldn't obtain the force versus time graph. The graph is fluctuating. Is there any possible way to get the graph using explicit solver?
It's all depend on the, like, without seeing the model, it's very difficult to answer that clearly. Like, I think he can contact me if we need anything, but I'm not an expert user for Abacus, but I can think about ways to answer his question if he clearly email me. I think I recommend you to email me directly so that I can go through more details and maybe answer that question. Any other thing? Or even comments like,
The audience here.
yeah.
I have a question. We are analyzing the blast from our
Yeah.
blast over, and because of the blast, the particles might hit the people different.
Yeah.
We are analyzing that part as well, so they are different domains.
Yeah.
So what are the capabilities of combining?
Yeah, this fragmentation is not well defined in FEA. Okay, now it's very difficult to get some like fragmentation effect from FEA yet. I attend this conference, one of the leading ones for shock physics area. Okay, now recently, like last week, even that one, they consider this is as a challenging exercise to model fragmentation in a blast event. Okay, but there are certain assumptions people have made based on the failures and other things. There are guidelines in UFC 340 and other places. What I'm recommending is now the structural failure you can capture, but it's very difficult to capture the fragmentation. So it's a judgment based on the failure. You judge like this is the possible fragment sizes and so on. I won't say it's already developed. Something I like to work in future as well, but it's a very challenging domain because fragment should like first thing is fracture mechanics should be well defined. Then all other physics, okay? Now, because if it's like come as small tiny particles, time steps and other thing will be a real problem. So it's not an easy thing. Because that's why I said like finite element has its own limitation. Okay, now there's no way that we can completely simulate 100% simulate the real world. Does that answer your question? Yeah. If I know something, yeah. If you want, I think especially even this recent conference, I found like people discuss about the fragmentation effect, but experimentally, but they found real difficult to model it in any FEA tool. They tried this SPH approach, but doesn't give that complete scenario. Okay, there are some consultants doing this using SPH technique, the particle method. So you model the structure with the particles. So particle represent material volume. So when the shock wave hits the building, particle displays according to the mass and everything, but it's not really representing the right thing. Yeah.
Because modeling the brain, what are the main properties of the input?
All this like brain, because if you see the skull material, it's total, it's like a brittle type material. Okay, so it's like a very close material is serum for skull. Okay, now then you go to the brain, it's like a jelly type material. So it's more like hypoelastic type of behavior. So you need to select right model like that. It's very difficult to get like say 1-0 give a 1-0 answer, but the brain, it's then around the brain you have a small liquid. You know, like this. I'm not a biomedical person, but there's a small liquid. So if you, I think we excluded that one, if I remember correct now. If you want to model that one, it's another small domain around the brain. So this is a very complex model. Okay, now there are certain assumptions we are making any model. So starting with the gel type of behavior in the internal cells, then you have the skull, even I think a skin, okay, thin skin, then the other parts, helmet and so pretty like we actually throw the ball at the 90 kilometers per hour type. Okay, now we use a bowling machine to create that miles per, no? Yeah, no, sorry. So you can find the right numbers, okay, in the paper. I can't remember, it's like old one. So we use a bowling machine to generate the velocity, and more than we expected initially with the approved helmet, it transferred the pressure into the skull. So in real case, we get that kind of impact. There's a chance that we get a serious damage. Maybe not fatal as in this case, but maybe a serious damage. You are unlucky, really unlucky. That is the can be side as well, like in that Bill Hughes one, that's directly impacted in the neck, right? Yeah, so it's a direct impact. So now what we tested here was like just to the helmet. We test without helmet, with helmet. And even one case I think we found that helmet got fractured to the velocity we checked. So yeah, interesting one, but we didn't go along that line to do more work and like fine tune this one. But our aim was it was like a hobby type of activity. Okay, now because of that big interest, okay, now wanted to do something with the undergrad project, so I defined. Any other questions, especially?
People at the back. Anything?
Please ask questions, otherwise not good. Anything in the online?
No, I think we covered.
Yeah. Exactly, yeah. So yeah, there's a big domain on that direction actually, especially the biomedical like areas. Even blast now, say shockwave hits a soldier helmet or some other. When we did the Kalpitia test, I think one of these users from army, they put some, you know, like fresh meat pieces near the blast source at certain distance to measure the shockwave effect into the cells of that meat, like, just to represent some, I think, of some like real world scenarios. So there's a clear interest on that shockwave impact into humans, like body or like even animals. Yeah. The real interesting area, and sport medicine and this area, like related to impact or blast or that kind of area, it's a good, real good research. All right. Okay, hope everyone there's like online as well as here enjoyed the talk. Okay, now if you have any questions, you have my email address here. If you are in Candy, I'm happy to meet you in Candy as well, and maybe tomorrow at my CH in a different topic. Okay, thank you very much. Oh, sorry, before I conclude, I need to thank Mr. Shiromal as well as all the team members for organizing this and inviting me. It was a tough tour for me. Okay, now it's a tough tour for me because I started in this one today and tomorrow different lecture, and then ending up with S3600 workshop 19th and 20th. So it's IHL. So hopefully see you again one day. So, okay, thank you.
As Dr. Damith said, he has had, I think he has a very tight schedule in the short trip that he's having here in Sri Lanka at the moment. And we are extremely grateful that he took the time to come and conduct this webinar for all of us. As we all know, these are free webinar series, and this is some very high level information that has been shared with all of us. So we're extremely grateful that he does this as a service to all of us, and that he is very supportive of the engineers in Sri Lanka as well. So thank you so much, Dr. Damith, for all of that. So to all of you, thank you so much for joining us today. And as you know, we will be running this webinar series. We have one every single month, and we do have the courses. We do have other events as well. So if you need to contact us, these are our contact details. Additionally, as I mentioned earlier, we will be having the CTBUH there will be a CTBUH event happening tomorrow. And once again, you will see Dr. Damith there as well, along with other professionals on some excellent topics. So if you are a high-rise building professional, we do encourage you to join. There's a lot that you can gain from it. So the YouTube link will be shared with all of y'all. So do keep an eye out for that. So thank you so much, everyone, and we will see you next time.